we have discussion about Faraday's law. So many times we have heard about Faraday's laws, and here we'll see that how it is important for us. Again, we'll see the Lenz law. Again, we'll see here about the transformer EMF, how it is being transferred from one to another. So let's begin with Faraday's law. I welcome all of you in this lecture. Okay. So now first we have discussion. So in case of a static magnetic field produces no current flow. Okay. So as per this Faraday's experiment, what was his observation? That a static magnetic field is not going to produce any current flow, but time varying field induce the voltage. So that induced voltage is called as electromotive force or EMF. So this is happening in case of closed circuit which occurs. So due to that, current is going to flow. Okay. So in case of a static magnetic field, no flow of current takes place, but in case of time varying field, flow of current takes place in a closed path. So finally, Faraday's law states that the induced EMF or induced EMF or BEMF that is given in the volt in any closed circuit is equal to the time rate of change of the magnetic flux linkage per linkage by the circuits. So by rate by which magnetic flux linkage is going to change, that is equal to the induced EMF. So here if you see that we have VEMF equal to minus d lambda by dt. So finally this d lambda we can write capital N d psi. So where this lambda is going to represent the flux linkage with the help of n psi, and n is the number of turns in the circuit. Okay, and this psi is here flux, total flux. Already we know about that. This is symbol we are using for the total flux. So now how many turns are there? So on the basis of that, it is multiplied with n. So that is going to give us the total flux linkage. Now we are going to see about Lenz law. So that is very important here. So now again here if you see that how this induced voltage oppose the flux producing it. So who is going to produce? They are going to oppose them itself. So the direction of current flow in the circuit is such that induced magnetic field produced by the induced current will oppose the change in the original magnetic field. So what is change is going to occur in the original magnetic field that is being opposed here by the induced current. So who is going to induce? Due to whom you are going to be induced, for them only is going to oppose. So sometimes if you see that nowadays in the modern day, a smart child, you can see a smart or you can say foolish child is trying to oppose many times to their parents, indisciplined child. So current is being induced and that current itself is trying to oppose the original magnetic field. So now here for that we have taken one small circuit here. So now here if you see that this portion represent the battery here. So inside the battery we have EF, that is the battery is going to produce this EMF, and EE is the due to electrostatic field. So finally, EF is available only inside the battery and EE is available outside in the wire also. So finally, what you're seeing here, when flow of current takes place, that electric field is in the same direction. And inside the battery, induced EMF due to battery and electrostatic field both are in opposite direction. So this is a consideration between this point P and N. Okay. So this battery is going to act as the source of the EMF. So this EMF is coming due to electrochemical action inside the battery. Okay. That produce the EF. and accumulation of the charge. So battery having plates, okay? So that accumulation of charge takes place at the battery terminals that gives us the electrostatic field that is given as E suffix E equal to, and this electrostatic field is related to the potential with minus del V. So now, so finally here you are seeing that we have total field, okay? So that total field consists of the EF plus E suffix E. So EF is due to the battery and this one due to the electrostatic field. So outside the battery, EF value is the 0, okay? And inside the battery, EF and E both are in the opposite direction. So finally here, the integral of the equation 2, we have E dot dl over the closed path, which is given as integral of EF dot dl over the closed path plus this 0. So here, that over the closed path, that integral of E dot dl is going to be 0 due to conservative nature of the electric field here. So we have only component that is due to the induced EMF between the point N and P, okay? And if we change the direction, then we'll have negative sign. Or if you'll again, if you keep the same direction and EF will want to write in terms of electrostatic field, then we have to use the minus sign since both are in the opposite direction. EF is moving upwards, okay, then direction of E is the downwards. So on the basis of that, here we are seeing that we have VEF, okay, this value VE, that is induced voltage, integral of EF dot dl between N and P is the 2 points we have seen earlier. Now EF is replaced by the minus EE, okay, and this is equal to IR, that is V equal to IR from the Ohm's law, okay. So finally, important facts, what we are getting here, that electrostatic field cannot maintain a steady current in the closed circuit. So finally here already we have seen integral of E dot dl equal to 0. So that IR also going to be the 0. So it's not going to maintain the steady current. And EMF produced by the field EF is the non-conservative. Since this is going to be, it's not going to be the equal. Okay, so it is EF is available only inside the battery. So already we have seen about the conservative natures and non-conservative natures, okay, in case of boundary condition also. So we have separate lecture for the boundary condition. So except in electrostatic, voltage and potential difference are not equivalent. So only in case of electrostatics, we are able to compare voltage and the potential difference, okay, but in other places, it is not equivalent. So here we have seen Faraday's laws and another is the Lenz law. Now we are going to discuss about this, how this transformation takes place here. So finally, you have seen here Faraday's law and Lenz law. Now we have discussion about the transformer EMF. So name itself is the transformer EMF. The transfer takes place, okay? So that is happening. We are taking here example of the stationary loop in time varying magnetic field. So B is here flux density, okay? And that loop is stationary, but field is going to change. So already we have seen by using Faraday's law, V EMF equal to minus dou psi by dou t. And if you are here n equal to 1, number of turns as taken as the 1. So finally, this equation 1 can be written as V EMF equal to integral over closed path E dot dl. And this one already we have discussion about total flux, that is the surface integral of B dot ds. So finally, here we can write these values. Okay. So here what we have expression BMF equal to integral over the closed path of E dot dl. And another what we have here term, okay, from the first equation, RHS is what? Minus d psi by dt. So this is what? Total flux. So that total flux is given as the integral of B dot ds, surface integral. So divide by dt. So now this LHS, this both are equal. So RHS is also going to be equal. On the basis of that, we got the equation 2 here. So now we can rearrange this, and this differentiation is taken inside the integral. So that gives us the equation 3. So now here this loop that is taken here. So here you are seeing that in this we have induced B, and this magnetic flux density is the time variant. Okay. So now EMF induced due to transformer action by time varying current in the SSA loop. So it is called as the transformer EMF. Why its name is given transformer EMF? Since it is happening due to the transformer action, due to the varying current in the loop. So due to that varying current, it's going to induce the EMF. So its name is given transformer EMF. So finally, we have by using Stokes theorem. So that Stokes theorem says that what is the statement of the Stokes theorem? So it have a relation that line integral of a vector is equal to the surface integral of the curl of that vector. So finally, here we can write integral of E dot dl over the closed path equal to del cross E surface integral. Okay. So finally, previous equation we have seen that we have integral of E dot dl over the closed path equal to minus integral of dou b by dou t, okay, into ds. This is one expression we have seen earlier. So finally now we are able to equate this. So finally here what you are seeing that we have, if you equate this equation, when it is really valid, when del cross E equal to minus dou b by dt. So this is also important relation that we need to remember. So this is the Maxwell equation in the time varying field. So here what we have, del cross E is not equal to 0. It shows that electric field is not conservative in time varying field. Whereas in case of electrostatics, we have del cross E equal to 0. So there we have a space variation. Here we have time varying. So these are the discussion. Okay. So finally, if you have any doubts, you can write in the comments, like, subscribe. Thank you. Thank you very much.